Thank you for being back. So now we have two contributed talk, and the first one is Qiaoya Wu about understanding the borderline region of Fujian.
Hi everyone, I'm Qiaoya Wu. I'm a currently PhD student from the University of Illinois, Urbana-Champaign. I work in fiction. So people may know me because I've done a lot of job on the Sloan spectral splitting of the quasar surface. But today I'm going to talk to you something different from the photoionization view of the broadline region. So first, I'm going to give a little bit background about the reverberation mapping. People already know that, I assume. So it's basically measuring the time lag between the continuum and the broad emission lines. And with the time lags measured, we know the distance from the broadline region clouds to the central supermassive black hole. And we can extract the velocity from the spectrum and combine the distance and the velocity. We can use some variable assumption and get the black hole mass. So with the reverberation mapping method, we find a very beautiful correlation between the distance of the broadline cloud and the continuum luminosity. So you can hear on the x-axis is the optical luminosity at 5100, and on the y-axis is the broadline size. So they have a very tight correlation between those two with like 1/2 proportional to the 1/2 of the luminosity. This is very beautiful. We got so many applications of that. One of the most important one I would say is the single epoch black hole mass estimator, because using reverberation mapping, it's like very expensive. You need a lot of like high cadence and long time monitor on the quasars. And with that, with the reverberation, with the single epoch method, you only need one epoch spectrum. And so we have the IO relation, we have the continuum luminosity from the spectrum. And with IO, you have the distance from the luminosity, and you can extract the full time maximum, the velocity from the spectrum, and using some of the major emission lines like the H alpha, H beta, magnesium 2, carbon 4, and you can get the black hole mass in a very cheap, very cheap and fast way to get that. And with that, we use that in the service, like what I've done. I measured like around 1 million, the mass of around 1 million quasars from Sloan, and I'm also expecting to do that for the data release 1. And we also do use this method for like high redshift supermassive black hole mass estimation. And here shows an example. So we decompose the spectrum into the host galaxy part and the quasar part, and we measure the weight of the broad emission lines, and we can get the black hole mass. And there's also another application that's we can use the quasar as a standardized candle to probe the cosmology. So you have the IO relation, you have the time lag you measured, and you have the luminosity, and you compare that with the absolute flux you get, and you can use that to compare with the lambda CDM. And here is some plots. So like it's very like they're very consistent with the current cosmological model, even though there's some scattering in the distance measurements, but it's a very like independent way to maximize our cosmological model. Everything is very beautiful. We got this like neat IO relation. However, during the past decade, we have way more RM measurements for the quasars, especially in Sloan, and also some other separate some campaigns. So this is the IO plot like a decade ago. It's very neat. The scattering is like 0.3, 0.2 dex, and now it's like very messy. So here is for the H beta distance, and you can see like the scatter is like around 1 for this IO relation. That can cause big problems in the single epoch measurement. And here's I'm showing the comparison between the IM measured mass on the x-axis, and the y is the single epoch mass. You can see that the scattering is like around 1 dec. That could cause a lot of trouble in the like for higher redshift supermassive black hole mass estimation. And so people think like maybe we can use some ways to correct that, and we can fix that. There are people that using some like the iron 2 to H beta flux to like try to tighten this correlation, but it cannot solve that, sadly. Like I would say that this kind of scattering is intrinsic, and there's no better way to actually resolve this issue. And I'm going to show you how that this kind of scattering the IR relation is intrinsic. And this could get even worse if you're considering the disk geometry, like we talked about earlier today, the like change from the standard thin disk to like the slim disk, the puffed up disk. So I'm going to get a very little background of the accretion disk, like the very easy one. So here's the thin disk model, the standard Shakura model, and that's a slim disk. So it's like the disk structure is totally different. In the thin disk model, it's like the height is way less than the radii and capillary, and the temperature profile across the disk is different compared to the slim disk model. And so we're going to start from the more easier ones here. So we'll be starting from the standard thin disk. So we first select some like AGNs with H beta reverberation mapping results. So the relative is relatively local. It's like less than 0.5. And we select their annual accretion rate between 10 to the -3 to 0.5. So it's not in the ADAF region, and it's not the accretion is not that high. So the disk get puffed up. And so here's the mass distribution, mass and the optical luminosity distribution for the 140 agents that we selected out. And there is their R relation. You can see there's like around like 0.5-ish dispersion on the R relation here in our example. And the color is for the UV spectroscopy. So I'm talking about that later. But so the black ones is those that we don't find the UV spectrum in the archival data. And so we are going to start using the SED for the standard thin disk model. So here I'm using the cursor SED model that was like Richard Goddess mentioned earlier. And so it includes three parts. One is the disk component, which is a multi-temperature black body, and the other one is a warm coronalized component that's added for the soft X-ray axis, and also a non-thermal power law component from the hot corona. That's the three main part for this model. And so when we fix the accretion rate on the upper panel, and you can see when the increases the mass, the overall SCD shape is almost the same. It's just like shifting the peak from the to a lower frequency, and the overall SED is like get more energy. And when we fix the black hole mass and increasing the accretion rate, you can see like the SED shape change, the alpha X change dramatically, and it gets steeper in this SED model. And we constrain the accretion rate to be lower than the log m dot is lower than 0. So I'm showing you an example. Since we're comparing the SED with the R relation, and we want to fix the x-axis, which is the luminosity. So I demonstrate an example. Like there are two separate SED. They have very close optical luminosity at 5100, but their SED shape are totally different. So the blue one has like slightly higher mass but lower accretion rate. So you can see that the green one has like lower mass and higher accretion rate. So they have very different SED shape, but they all have the same optical luminosity, which means they would have roughly at the same place at the same vertical line at the RL plot. So and you can see that in this kind of the SED shape is very different, and the very different part is like in the soft UV part is like 10 to 100 EV, and that's where most of the UV emission lines are ionized, because the ionizing potential is around like 50 to 60-ish. So we would focus on the UV spectroscopy in our demo. And so we propose like 50 SDSRM observation from the Sloan HST states, and also we got some 52 for the local agents from the HST and IUE archival spectrum. So with all that spectrum, we generate the composite UV spectrum for the archivals and the proposed agents we got. So you can see we match their optical luminosity at a small range, and we composite them. And you can see here, like the green one, I put a zoom in version. So the green one have a slightly higher accretion rate, and their Lyman alpha line strength is way stronger than the blue one, which is consistent with this plot, like because they have the green one. It's not the same, exactly the same, but that this part is for the illustration. So the green one have more ionizing, have higher accretion rate, but lower mass, and they have the same optical luminosity, and they have more ionized energy at the hydrogen part. So, and we got the SED, so we want to compare the flux, the UV emission line properties that we observe. So we use the cloudy, and we adopt the locally optimally emitting cloud model to compute the line flux. So here is the continuum luminosity. So on the background, it's our prediction from the SED and the cloudy. So, and the data points are the observed continuum. So you can see the continuum is very consistent. And I have to know that, so the SED, the cursor SED model, it uses the accident scaled accretion rate, but here we are not using that M dot. We are using the accident ratio as we computed in the observation, which use the optical luminosity plus a correction factor, the volumetric correction factor, and divided by the accident luminosity. So here is the continuum, and here we compare the major, the equivalence weights and also the line flux for the major emission line. So they were like generally consistent with each other. Yeah. So after we got our photoionization model, we want to compare like our photonized predicted our relation with the observation. So we assume that all the broad clouds in our, so the broad clouds in our model have the same ionizing parameter and the same hydrogen density, and we got this prediction of the broad size. So you can see like in each being, each being is different black hole mass, and the stripe in the background is our prediction, and the data points are overlaid on the each subplot. And so in each subplot, you can see at the fixed mass, the broad side would increases with the accretion rate, and yeah, they were very consistent with each other. So we got some good news that we successfully reproduced the error relation with the SSC model, standard synthetic model. However, this kind of scatter is intrinsic in the error relation, because different black hole mass and different accretion would lead to different SED, and that SED could cause the scatter in the error relation, like showing here. And even though we successfully reproduced that, we want to look into our data, but we find some issue with that. So this is the observed IR plot for our AGN sample. We divide them into different beings based on their optical luminosity, and we'll plot them here. So here is our plot, and here on the y-axis is still the time lag, the distance, and on the x-axis is accretion rate. So you can see the black line is our prediction. Our prediction shows that as the accretion rate at the fixed optical luminosity, as accretion increases, so the distance should be increases. But you can see that in the observed data points, there seems to be like a or like a decreasing trend in the observed data, which is not what we expected, but we have some explanation for that. So first is like we use the HSD that's mostly based on it's standard synthesis, and so the accretion rate is limited, and also the hot and the warm corona component is fixed in this model. That may cause some trouble, and also in our assumption, we assume that the hydrogen density for the polarization cloud is fixed, which may not be true, because we find that if we increase the hydrogen density with the accretion rate, that problem could solve. We could find the decreasing trend, but we have no way to quantify that. So that might be a reason that we see this opposite trend in our prediction. And also, if you considering the self-shadowing effect, the change of this geometry, the things will get even more messier. But it could still explain the kind of decrease trend that we see in the observation. So, though as I mentioned, like in the higher accretion example, the disk would puff out and become a slim disk. And here, like there's a RM campaign that only at the super accretion rate quasar, and you can see like that's a traditional IO relation, and their example shows that there's like a significant offset from the traditional IO relation. And here I plot all the localized local agents with the H beta RM measurement, and you can see for the higher accretion rate example, all of their accretion rate are lower than the the black line. That's the RO rate, and that is partially because of the change of the disk geometry. You can see like so when the accretion increases, the disk puff up, and the clouds roughly at this region, they may not be able to see the higher ionizing photons coming from the inner region of the disk. That part of the radiation is blocked for those polarization clouds, and so they receive less radiation pressure that can so they would be more centroid to the supermassive black hole. That makes the distance like smaller. The distance is smaller, so in the R plot they have the offset from the canonical R relation, and so we did some preliminary results. So we're trying to find some the UV spectrum for those higher accretion requests, even though there's not too much. So you can see when we increase the accretion rate from like lower to moderate or higher accretion rate, so the H alpha strength it first increases, and then when we increase the accretion rate, it decreased, which is surprising. But we don't have enough UV spectroscopy to show that this is a composite spectrum. We don't have enough UV spectrum to quantify that right now. So we propose the HST observation on like more than a dozen of the higher accretion rate quasar, and we're waiting for the observation right now. We hope that if we got more data, we can still find this significant change in the Lyman alpha strings. And so here's the toy model. We think because when the accretion rate increases, the this geometry change. So the photons, the higher energy photon come from the inner part of the disk are blocked. That might explain why we see the decrease in the Lyman alpha line strings, but we're still waiting for our data, and they will probably will get some results later this year. And that's all I have for today. So first, we have this beautiful ion relation, which help us a lot in the survey and hide the black hole mass estimation. And there's a large intrinsic scatter that I find in the SSD model, because probably due to the difference in their SED. And also, our prediction shows that our prediction is actually kind of opposite to the observed trend, which may be due to a lot of reasons, like self-shadowing or like some assumption in your SED, or maybe something with a standard synthesis model, or like the gas density may not be uniform in the cross AGN sample. And we will need a better AGN model for AGN model or disk model to resolve this issue and to better study the line emitting regions. Thank you.
Thank you. We have quite a lot of time for questions.
Yeah, hi, really nice talk. I have a question about this cloudy simulations and mostly about this higher accretion, because I know that in cloudy you can also change like metallicity or you fix, and do you think it would make sense to a bit explore a bit different range of metallicity or not really?
So in the RL plot, it's not really like the metallicity wouldn't change our result, but it would change the line flux we predicted.
So I'm a little confused about your comment about how the line strength changes with the accretion rate, right? So like a weak line quasar has equivalent widths of maybe less than 10 angstroms in carbon-4. So are you saying that those are not the highest accretion rate objects, or those are the highest accretion rate objects?
So you mean the F a carbon-4
The highest accretion rate objects still have the lowest equivalent widths.
for carbon-4? Not really.
I think it's moderate accretion.
Yeah, accretion are in between.
Yeah.
So, I mean, what would you predict the accretion rates are for like weak line quasars? That, I mean, would you call that low, moderate, or high?
Weak.
Like, things that have like 10 angstrom carbon-4 that look nothing like any of those three things you're showing.
This is probably in the higher accretion rate quasar part because I assume that the disgeometry change, so they don't have enough the ionized photon to ionizing the carbon-4 that leads to the weaker.
Maybe I have a comment about your model and the versus relation. This one, yes. So if I understood correctly, this is flattening or deviating from the classical one, especially at high luminosity.
So the green one is from the classic.
Yes. So you are finding smaller sizes at the high luminosity.
Smaller size, you mean the, yes.
The smaller sizes at high luminosity. So the effect would be to have smaller black hole masses at high luminosity. And so if you derive the Eddington rate or the accretion in this way, there would be even more super Eddington.
Yes.
So smaller black hole masses for the same bolometric luminosity, it means super Eddington. I mean, higher Eddington ratio. So my question is, a change in this relation that goes in this direction doesn't help us in reducing the super Eddington accretion for the Eddington sources. It makes the problem even worse.
Yeah.
Okay.
I have a small question. On your slide 11, you show this SED figure where you vary the Eddington ratio. Oh, yeah. So all the lines are intersecting at around 10 to the 18 hertz. Is there any special about this?
So it's mostly because of in the QSOSD model, the hot and the warm corner component are kind of fixed in that model. So the total luminosity changes, but the electron temperature, the slope is fixed in that. So that will cause a intersection over there, but that may not be real, that not be real.
And question on this topic. Yes,
I didn't quite understand the Lyman alpha explanation. I know it's difficult to model, and so you have a feeling for why the Lyman alpha? It's not monotonic, first of all, but I guess it gets stronger again, which is intriguing. I don't want to put you on the spot. If you don't have an explanation, it's okay too, because Lyman alpha is very difficult to model. But do you have a feeling for why? I mean, that's the observation. Right.
Yeah. So we think it might be because of SED, the shape, the ionizing and the energy at the 36 EV is changing. It's not like changing only in one direction, probably and then it drops.
Oh, that's what you're
Yeah,
showing there.
that's roughly.
Okay. I think we can thanks Qiaoya again.